Thanks, Joe. All right, so today in my talk, I'll try and convince you of three main points. I'll try and convince you that massive early type galaxies are not passive dead systems, so they have widespread star formation. I'll show you that the star formation is largely driven by minor mergers and adds about 20 to 30% of the galaxy's stellar mass after redshift of 1. And I'll show you some preliminary work that we're doing which suggests that this star formation, this minor merger driven star formation, is not strongly regulated by AGN feedback. Okay, so early type galaxies have been studied for a while, so most of what we understood about these galaxies came from optical astronomy for obvious reasons, because optical data was most abundant. So if you look at early type galaxies in the SDSS, so these are early type galaxies selected by visual inspection of SDSS images. So they're morphologically selected and they are low redshift early type galaxies. Okay, so everything here is at redshifts less than 0.1. So if you plot the optical G-R colors of these early type galaxies, then you get red colors, very little scatter, right, which tells you that the bulk of the stellar population in these galaxies, or perhaps 100% of the stars in these galaxies, are old, right, so formed at redshifts, let's say 2 or 3 or above. But when you plot the same galaxies in the UV optical colors, right, so you take these galaxies, which have red G-R colors, and you plot them in the NUV-R color. So the NUV filter is the near ultraviolet filter from GALEX. So this filter is centered at around 2300 angstroms. And what you find is that the same galaxies show 6 mags of spread in the UV color. Okay. So what this tells you is that there are strong UV sources present in early type galaxies in a low redshift universe. Right? So now that doesn't necessarily tell you that that's driven by star formation, because you can have core helium burning stars on the horizontal branch which can also pump out a lot of UV flux. However, I'm not going to go into details here, but it's fairly easy to show that the UV that you would get from old stars, even if you assume maximal contamination of the UV spectrum from these core horizontal branch stars, it's not really enough to give you the kind of scatter that you see in this diagram. Okay, so essentially old UV bright stars do not pump out enough UV flux to make your early type galaxies as blue as we see in these GALEX SDSS colors. Okay, so most of this UV flux is driven by star formation. So if you wanted to put a lower limit, so for example, if you assume that every single early type galaxy here has a UV upturn, which is the UV flux which is driven by old stars, equal to the strongest UV upturn galaxy in the local universe, then you can reproduce everything except for the bluest 30%. Right? So at least 30% of early type galaxies must have young stars to satisfy these UV optical colors.
But to be fair, the G-R colors have a full range of a half.
Yeah.
And so that is an enormous spread and much larger than any quiescent selection would entertain.
Agreed. But the point is that you can't measure...
This has a bunch of star formers that were already known from optical in it.
That's true. But the fraction that you would derive from the G-R color will be much smaller than when you look at the UV. Because the UV is more sensitive.
Have you looked at the FUV minus NUV colors on these?
Yeah, so we looked at FUV minus NUV, FUV minus R. The reason I'm not showing you FUV here is because the FUV detector was basically non-operational for large parts of the galaxy. So we just have less data. But if you plotted FUV minus R, you would see exactly the same.
Right, because you can look at an FUV minus NUV map of like M31, and you can see that the bulge is a radically different color than the outskirts, which gives you some constraint on the fraction of.
That's right. That's a good point. So if you look at the FUV to NUV slope, the UV upturn goes mainly into the FUV, right? So the old stars put most of their flux into the FUV, whereas if the UV is coming from star formation, then it's flatter, right? They go into both the FUV and the NUV. So you can constrain how much of your UV flux might be coming from old stars by looking at the FUV-NUV slope. And if you do that, actually you find that hardly any galaxies are consistent with purely UV upturn. So all galaxies really need a star formation component. Okay, so we have this degeneracy in the low redshift universe, right? So you can have UV from old stars, you can also have UV from young stars. So one way to get around that problem is to push your analysis to high redshift, right? So if you go to a redshift of, let's say, 0.5, then essentially the universe is too young for these old stars to be in place. Okay, so the horizontal branch takes about 9 billion years to kick in, right? So if you perform the same analysis at a redshift of, let's say, 0.5, then essentially the horizontal branch has not really developed. Okay, so any UV that you have is likely to come from young stars. In other words, the UV becomes a much cleaner indicator of star formation at these intermediate redshifts and higher. Okay, so what I'm showing you here, so this is the Galax plot that I just showed you in the last slide, and this is the equivalent plot of early type galaxies in CDF South. Okay, so these galaxies have Cosmos 17 redshifts between 0.5 and 1. They are selected visually via HST images from the GEM survey, and we've constructed a rest frame NUV minus R color, so you can compare it directly to the Galax results, from deep U and B band imaging from a survey called MUSIC. So what you find is that the situation doesn't really change, right? So what you see in the low redshift universe, you also see in the intermediate redshift universe, right? And if you do SED modeling, you find that the mass fractions of stars, so each event that creates the star formation is adding a few percent of the stellar mass to your individual galaxies, right? And this star formation is persistent across this entire redshift range. So from 0 to 1, you have persistent star formation in early type galaxies, which are fairly massive.
Persistent in a statistical sense.
Right.
Yeah. Right.
Sorry, can I ask a quick question?
Yeah, sure.
When you say they're selected visually, do you mean like by eye, you look at it
By
and see
eye.
if it looks like a
Yeah,
bulge?
yeah, right. So we found, so actually Kevin and I did most of the visual inspection where we found that if you select early type galaxies, let's say by color, then you miss out all the interesting ones, essentially, right? Because so you shouldn't make a prior assumption about their star population. Okay, so we have star formation. So the next logical question to ask is what drives the star formation, right? So what is the source of gas which fuels the star formation in these early type galaxies? So there are several sources of gas. So the obvious one is stellar mass loss, right? 30% of the IMF will eventually come back into the interstellar medium, and some of this gas could fuel star formation. In the case of the low redshift early type galaxies, though, the part of the gas which you're looking at, or the relevant part of the stellar mass loss, is the stellar mass loss that happens at low redshift, right? So you're looking at the gas which is coming back in around the last gig year or so, right? So if you do a sort of a self-consistent chemical enrichment modeling, it's fairly easy to show that the stellar mass loss around the redshift of 0 is not enough to produce these UV blue colors. Okay, so you don't put out, you're not pumping out enough gas into the interstellar medium in the recent past to give you the UV optical colors that you see. So stellar mass loss is unlikely to be fueling the star formation.
You haven't told us how much star formation you're seeing.
So it's a few percent in mass fraction, right? So about 5% of a 10 to the, let's say, 11 solar mass galaxy in the last gig year.
You have to give me a time scale, otherwise it doesn't make sense.
So in the last gig year, I'm producing 5% of the stellar mass of a 10 to the 11 solar mass galaxy.
Can you give us a specific star
So
formation?
it's about 1 to 2 solar masses a year.
Specific.
Specific, well, you divide that by 10 to the 11.
But the star formation rate cannot be 1 solar mass per year, right? That's ruled out for most early types.
No, I disagree. So if you look at the blue early types, the ones which are in the
The
UV
blue ones,
cloud,
but almost all of them are red. And
well, the blue early types, let's say 30% of the early type population, which is in the UV blue cloud, have high star formation rates, right? So if you look at Fukujita's paper,
understood,
they
you
are
call them
10 plus.
early type spirals with big bulges in the local universe.
These are not spirals with bulges. These are elliptical galaxies. I mean, I can show you images. They look perfectly elliptical. There's no disk structure whatsoever.
30% blue spheroid fraction at high mass sounds really remarkable if true.
Well, it depends on the mass range you're looking at, right? So they're not all 10 to the 11 solar mass galaxies, right? They have a range in mass. They have a range in luminosities. Okay, but these guys have high star formation rates. They have Milky Way type star formation rates, right? So these star formation rates are not negligible, and you can't. So this is the point, right? You can't really measure this kind of star formation rate from the optical necessarily because you just don't have the data in the ultraviolet, which is where most of the young stars are putting in their flights. Okay, so what drives the star formation? So stellar mass loss is unlikely, but if you look at the literature, there's actually a lot of circumstantial evidence that the gas in these early type galaxies is accreted from an external source. Okay, so for example, When you look at gas and stellar kinematics in surveys like SARA and Atlas 3D, they are often decoupled. Okay, so the gas kinematics doesn't follow the kinematics of the stars, which tells you that the gas doesn't come from the stellar field. Okay, because if that was the case, then you would have a tight coupling between the gas and the stellar kinematics. When you calculate dust masses from the infrared, you find that dust masses in early type galaxies, especially the star-forming early type galaxies, far exceed what you would expect from stellar mass loss. If you look at early type galaxies in fairly deep imaging, so this is, for example, work done by Sokyong Lee and Peter van der Koom and Kevin and others, what you find is that a high fraction of early type galaxies are morphologically disturbed. Right? So you can't see the morphological disturbances in standard depth SDSS imaging, because standard depth SDSS imaging is actually very shallow. But if you go slightly deeper, you start seeing evidence for these recent interactions. And then there are young kinematically decoupled cores in early type galaxies, which are signs of recent mergers. And these are actually quite abundant in surveys like SARA and Atlas 3D. Okay, so one way of trying to quantify this problem, or quantifying this issue, is to look for a coincidence between UV blue colors and the presence of morphological disturbances. Okay? And you can do this with deep HST surveys like, for example, Cosmos. So what we're doing here is we looked at the early type galaxy population in Cosmos. Okay, so these are images, HST images from the Cosmos survey, and we tried to separate early type galaxies, so things which are Bose dominated, had fairly smooth light distributions, into things which were relaxed and things which had morphological disturbances. Okay, so you can see that you have material flowing in here, they have fans, tidal debris, shells, etc. And we asked the question, what are the UV colors of this subpopulation of early type galaxies compared to this subpopulation of early type galaxies, right? So are the UV colors of relaxed early types significantly different from the UV colors of the disturbed early types? Okay, so if you plot the histogram of rest frame UV color, so this is NUV minus G, observed U minus I essentially. So this is all in the Cosmos field. So the relaxed early types are here. It's the black histogram. And the disturbed early types are shown by the gray histogram, right? So you see that the color completely separates. So if you have a morphological disturbance, which you can, and the best way to work out if you have a morphological disturbance is to look at deep HST data, because you then have both the angular resolution and the depth to do both morphology and tidal debris analysis at the same time. If you have, what you find is that if you have an early type galaxy which has a morphological disturbance, it also tends to be UV blue. Okay, so there's a...
Do you have this plot the fixed stellar mass or?
As fixed stellar mass, no, I don't have it, but it's easy. So there seems to be a correlation or a coincidence of disturbed morphology and UV blue color. Okay, so this suggests then that the UV colors, the blue UV colors, are driven by mergers. But when you look at the major merger rate at low redshift, right, so these are mergers, say, at redshift being 0 and 1, what you find is the major merger rate is quite low, okay, and it's too low to satisfy the fraction of disturbed early types that we see. So what that suggests then, what that leaves you with essentially, are minor mergers. Okay, so we've heard a little bit about minor mergers. So it's likely, based on what we've done with GALEX and the CDF South data, that at least 60%, and perhaps up to 90%, right, because there's a scatter in the observed or the empirically derived major merger rates. So at least 60% and up to 90% of the events which are driving the star formation in these early type galaxies are likely to be minor mergers. Okay, so I've talked about star formation and what drives it, so let me come to AGN. So we think that there is widespread star formation in early types since redshift 1. A significant minority of the stellar mass is probably being added to these galaxies after redshift 1. And there's evidence that this star formation is being driven by mergers, but there aren't enough major mergers to satisfy what we see in the data in terms of the fraction of disturbed ellipticals or early types. So it's likely that the star formation is being driven by minor mergers. And an interesting aside, if you look at the late type galaxy population, because minor mergers are not restricted just to early type galaxies, they happen, all massive galaxies of all morphological types are accreting satellites. It's actually fairly easy to show that a significant fraction of the local staff mission budget is driven by this minor merger process. Okay, so this is a process that we don't understand, and there are good reasons why we don't understand it, is because finding a sample of minor mergers is hard, right? So if you try and do minor merger studies via closed pairs, usually the bigger guy in a closed pair has a spectroscopic redshift, but the smaller one doesn't, etc., etc. So we haven't really studied the minor merger process in detail, but we should. So they don't just affect things like sizes, they affect staff formation and the staff formation history of galaxies as well. Okay, so let me finish off by showing you some preliminary work on AGN. Okay, so the question is, do AGN regulate the staff formation that I'm talking about? So what you need to do then is you need to combine indicators of star formation, like we've got here, galaxy and SDSS colors, with indicators of AGN, right? So people have done this kind of stuff before, but AGN identification can be somewhat difficult, because if you have, so typically people look at things like BPT, so emission line diagnostics, from which you can cull large samples of AGN from surveys like the SDSS. So nuclear activity can be obscured, so that might stop you from identifying some AGN. Emission line AGN don't necessarily correlate with radio AGN, right? So models postulate feedback via jets, which are best detected only in radio. So we have radio surveys like FIRST and NVSS, but they don't necessarily, or they don't resolve the cause of the galaxies, right? Where the AGN emission is from. And so contributions from star formation and AGN are sometimes hard to disentangle in FIRST and NVSS, right? So typically what you try and do is you try and look for excess radio flux above what you would expect from star formation, which skews you towards AGN, which dominate the star formation. Or you have to be in a dense gas environment where the AGN does work against the gas and produces detectable radio lobes, right? So that biases you towards galaxies in groups and clusters. So one alternative, which has some benefits over these methods, is VLBI. Okay, and there's an ongoing large VLBI survey of the SDSS called NGIVE 20. So NGIVE 20, or NGIVE, is using VLBA filler time. It's looked at 20,000 plus first sources and has made more than 4,000 detections. Right, so the good thing about VLBI is that it can identify, so given enough sensitivity, it can identify AGN unambiguously, because the high resolution requires temperatures of 1,000,000 Kelvin or more for a detection, right? So it picks up the radio, it picks up the cause of these AGN. Okay, so the question to ask is that, is there evidence for AGN quenching in these VLBI detected early time galaxies? Okay, so here's the U-R color of early time galaxies, U-R versus G-R, and the black points are the VLBI detections. Okay, so these are the guys which have the radio AGN. So the first thing you notice is that these guys are all restricted largely to the red sequence. So let me switch to a more star formation sensitive color.
I don't see that. I think it's more or less the same distribution. Yeah. Maybe it's slightly, but it's not variation.
No, if you look at the blue to red ratio, it is actually different. It's hard to tell from this plot, but it is different. So let me switch to a more star formation sensitive color. So this is NUV-R, and this is U-R, and the situation doesn't really change. So things get stretched out in the color plot. So the point here is that these AGN, what you have to compare is the transit time from blue cloud to red sequence to the typical lifetimes of AGN, right? So if you have typical lifetimes of a few times 10 to the 7 years, the transit times from blue to red are significantly longer than that. Okay, so the transit times are roughly a gig-year or more, and so it's unlikely that these AGN started off when the galaxies were in the blue cloud, right? Because the lifetimes are not long enough for these AGN to survive the transit from blue to red. So AGN, in other words, don't seem to be
constraint
dropped.
on the radio AGN lifetime?
Say again?
Do we have constraints like that of radio AGN lifetime? I understand that for quasars, you argue that they don't last for more
there's
than
been
30
work
billion
on,
years. But
there's been work on AGN lifetime, yeah.
so I can't have low-level radio.
You see these multiple generations of bubbles, and that's what it is determining some
Right.
radio.
And that's an upper limit. You just can't do it for longer. That seems
So let me wrap up and then we can come back. So AGN seem not to be prompt. Okay? So Kevin found the same kind of thing using X-rays, using Swift BAT. So if you work out the, so if you try and work out how big this time delay is, right, so you divide the age of the starburst in these AGN detected galaxies, or radio detected, or VLBI detected galaxies, and you divide it by the dynamical time of the galaxy, it gives you a normalized quantity that you can use to compare galaxies that have different radii and masses. So what it seems, or what this analysis seems to be telling us, is that the AGN has triggered several dynamical timescales into the starburst episode. Okay, so the gas reservoir, so when the AGN switches on, the gas reservoir is already significantly depleted. Okay, so the role of the AGN in regulating the star formation is diminished. So these are cold mode AGN, right? So these are AGN which are triggered by mergers, because the star formation is merger driven, minor merger driven. So I'm not talking about hot mode AGN, which are triggered by cooling of hot gas, either by cold flows or from the internal hot gas reservoirs of these early type galaxies. So these hot mode AGN do produce feedback, as we've seen. Okay, so this is my summary. So there are no truly passive galaxies. There's widespread star formation in early types and late epochs. The star formation is likely to be driven by minor mergers, and we should study minor mergers more as a process. And the VLBI analysis that we're doing, and this is ongoing work, it's preliminary, suggests that these cold mode AGN, which are fueled by these minor mergers, do not appear to be regulating star formation particularly strongly, because they are essentially kicking in too late into the starburst episodes. Okay, so they're not prompt enough to couple to the gas reservoir while the bulk of the star formation is actually taking place. And I'll stop there.
Could this just be a selection effect against the cold mode AGN? I mean, you are pre-selecting objects based on, VLBI detections. Perhaps you're selecting against cold mode AGN.
Against hot mode, you mean?
No, against cold mode.
Against,
Also,
yeah.
Well, I have cold
Against
mode,
cold mode.
but most of my AGN are cold mode. Right?
How do you know?
Why do you think that?
Okay,
The radio
so-
selected.
Yeah.
Radio selected,
usually we associate that with hot mode.
So let me show you, right, so this is something
I'm
that,
thinking the same thing as you, right?
so let me show you the properties of these AGN based on Frank's environment catalog. Okay, so these are, so this is stellar mass versus halo mass, so this is from the Yang et al. Catalog. So we're still trying to work out what type of AGN these are, but most of our galaxies are in groups in the field. Okay, so if you look at the halo masses, they're in groups in the field, and they tend to be at fairly large group-centric radii. So even the ones which are in large halo masses tend not to be centrals, essentially. So that's the rationale behind suggesting that it's not a hot mode AGN. Okay, and the other thing that we've done is we've looked at, we've visually inspected the sample, the VLBI detected ETGs, early type galaxies, and we've worked out what the merger fraction is in the VLBI detections compared to the general early type galaxy population. And what we find is that the merger fractions are elevated by factors of 3 or 4 or more, actually, irrespective of environment.
That's an interesting result.
So if there is so much star formation, you say that it's associated with minor mergers, I would expect to see kind of relatively strong color gradients.
Yeah,
But,
yeah, we haven't looked for that.
usually every time we see the optical galaxy, we don't have some.
Well, if you look at HST imaging of minor merger remnants, you do, actually. You find not just color gradients, you find a lot of structure in colors. So let me show you very quickly. So this is what your typical early type would look like if you had a minor merger, right? So this is a study we did a few years ago. This is Crockett et al., 2011. So this is an HST, this is WIFC3 imaging of 4150, which is a smallish galaxy, but it has a kinematically decoupled core, which has young stars. And so not only do you see color gradients, you see a lot of structure, but you need to have high resolution to see it. Because the minor mergers, most of the action happens right in the core of the galaxy. Right? So you're not looking at something which affects the galaxy as a whole. It doesn't go up to, say, 1 effective radius. It's restricted to maybe RE divided by 5 or 10.
And the other thing is that I would really divide the sample at least in lower masses, higher masses, because as we saw that they are really kind of two different populations.
Yeah, I agree with that.
And they share this rotational component, they have to
Yeah. But if you divide the samples into, let's say, 2 mass bins, the effect doesn't really disappear. You still see star formation if you look at the UV colors.
We're gonna work our way around. Knut?
You might have said on the last content slide that AGN only gets triggered after a couple of time scales, after it gets started too late. I could follow the argument why you consider that.
Okay, so so if you look at the position of these, the VLBI AGN, right, they tend to be on the red sequence, right? So if the AGN lifetimes are, let's say, a few times 10 to the 7 years, and it takes you a gigayear to transit from blue cloud to red sequence, if the AGN was triggered promptly when the starburst started, right, and the galaxy was in the blue cloud, then the AGN lifetime would have to be similar to the transit time from blue cloud to red sequence, essentially. Right, so AGN lifetimes are much shorter than the time it would take you to move from the blue cloud to red sequence. If you quench star formation completely.
Cycling, right? You can have a bunch of episodes of activity over a billion years.
Yeah, but you would still see that there's no reason to not see the AGN when they're in the blue cloud. Right? Even if you trigger and re-trigger, come back down, it doesn't matter. Unless the lifetime changes for some reason as a function of the color of the galaxy. Right? So there's no reason why the blue to red, so the blue to red ratio here is lower than here.
There's a strong dependence of the jet lifetime to the luminosity of the jet, so you can have easily up to 100 megayears lifetimes.
Yeah, so if you have long lifetimes, then you could, it would probably change the results.
Okay, I think, sorry, just a couple of questions, but I think we should thank our speaker.